Thank you very much. Thank you all for coming. My name is Martin. I'm DevRel at Avalanche, and I'm going to talk about cross-subnet communication today. Just to get a quick feeling for the room, who here is more or less familiar with the concept of subnets? I see one hand, 2, 3. Okay. Okay, we're going to do a quick recap on what subnets exactly are and why we need cross-subnet communication. Right? So when we talk about blockchain systems, we can have certain metrics to, like measure their performance. And when we look at, decentralization, we can do all this kind of stuff. But I just want to look at performance, right? So at throughput and time to finality. And I usually take this analogy of a highway, right, where you think of a blockchain as a highway that has multiple lanes. Cars can travel through it, and it has, like it takes some time to go from the source where you are to the destination, right? So every car on this highway is a transaction. We can have very, very long highways. We can have very, very short highways. At the same time, any highway can be very wide, have many lanes, or very narrow and have only a single lane, right? And these two metrics are not related to each other. It's very important to understand that time to finality in blockchain systems and the throughput of blockchain systems are not necessarily related to each other, right? So when we look at common blockchain systems, we can have high throughput systems and with a short time to finality or a long time to finality. If we look at Avalanche consensus, what they achieved is, the engineers there, is we have a short time to finality and a wide highway. If we compare it to other chains, right, like Bitcoin or Ethereum, Bitcoin has a very low throughput, but still a very high time to finality, right? So it takes very long, and we only have a few transactions per second. Ethereum is kind of like the middle ground, and Avalanche. But let's look at Avalanche now, and we see we achieve very short time to finality. We have a reasonably large throughput, but that throughput will never be enough to cater to the next billion people. Right? So now we can introduce all kinds of new technology innovations, ZK, right, to try to make that highway wider and wider. But what we figured out at Avalanche is that no matter how wide we're going to make this highway, with whatever technology we're going to use, we will never make it wide enough. Right? There will be no way that we can scale to billions of users for IoT devices, for all kinds of devices, with these mass transactions with a single highway. That's why we created the subnet architecture. So the subnet architecture means that we have the primary network, the P, X, and C chain, right? Every validator is validating that. But then we take a subset of the nodes, right, the subset of the validators, and they validate independently of the primary network another chain, right? And these these validators, they might also validate multiple chains. And there might be completely distinct sets, right? Like you can see here, subnet 1 is validated by some validators, subnet 3 is validated by some validators. They don't share any validators, still there in the Avalanche network, and all of them are validating the primary network. So this is the approach of scaling in Avalanche. And if you look what that means, kind of with the analogy that I just presented, is that each of these subnets has blockchains which are their own highways. So we want to build a highway that is incredibly wide, that can serve to many, many cars at the same time, but still we want to keep it short, right? We don't want to lose time to finality, and we don't want to gain scalability at the price of time to finality. Therefore, we think like this app chain approach, the subnet approach, this architecture here allows us to scale indefinitely with all these subnets. Is that clear so far? Does anyone have any questions so far? No? Okay, cool. So scalability does lead a little bit to fragmentation, though, right? So we have these highways now. They're independent blockchains. We can have as many as we want from them, but we need to make them interoperable. And this is what this talk is about. And we're going to explore how we can send a message from one chain, from the source chain, to the destination chain using Avalanche Warp Messaging and Teleporter, right? So what does this even mean, sending a message, right? So any interoperability between blockchains comes down to sending a message that is proving something happened on the source chain to the destination chain. This could be all kinds of things. This could be, I'm voting on a DAO proposal on the source chain. I'm depositing some ERC20 tokens, so I can claim some new ERC20 tokens on the other side of a bridge, right? All kinds of stuff. This could be cross-chain liquidity, right? But it all comes down to sending messages in a secure manner from one chain to the other. So yeah, as I said, we have asset bridging, we have DAO voting, we have cross-chain liquidity, but it may also be that we want to access resources that are only available on the destination chain. Chainlink oracles, Chainlink functions, CCIP, all kinds of stuff, right? So this is what we're going to look at. This is what we're going to try to achieve. And we want to achieve this. It's really easy to achieve if you don't care about trust, if you don't care about load. But we want to achieve this in a trustless manner. And that's what we're going to talk about today, right? So the first thing is, and this is like the most important part, is the security of cross-chain communication. And I'm going to do like a little recap of cryptography. Whoever did a bachelor in computer science might have nice memories coming up. Whoever doesn't have one now gets like a crash course in cryptography. So what we talked about with the messages, it's not hard to send a message from one chain to another chain, but we want 3 properties for these messages: authenticity, non-repudiation, and integrity. So what does that mean? Authenticity means whoever sent the message, we can be sure that this person really sent the message, that it's not coming from someone else, right? I send a message, you guys can be 100% sure that it originates from me, and no one else can claim that the person is me. Non-repudiation means when I send a message to you guys, I cannot go back. I will not have the chance to, claim at a later point that the message is not from me. I have a commitment to this message. And the last one, integrity, means when I send a message to you and someone helps me deliver that message, that person can't change anything about the message. The message stays exactly the same. So how can we achieve this? We use something called signatures. You might know it, like from the real world where you sign a contract or something. It's not exactly the same because technically, you can change something about the contract after, you can make some notes on it, but generally it's meant on a commitment from you and the other party that signs it to that, whatever it says, right? And that it won't be changed after. So this is the idea. We take a message and we attach a signature. And these signature schemes have 3 operations for us, right? So you might know it if you use the wallet, they also use signatures and everything. We have key generation, right, where we create a public key and a private key. These 2 belong together. I can publicize a public key. Anyone can know it. The secret key I'm keeping to myself. I also have a sign function where I take a message and my secret key, and it produces a signature, right? I am the only one who knows my secret key, so I am the only person capable of creating the signature. And I have a verify function. I can take a signature, I can put the message of the signature, right? Only these 2 have to belong together. And the public key that belongs to the secret key that I signed, the signature was created with, and I can verify it, right? It will give me 2 possible values, true or false. If someone changed the message, if someone used the wrong key, right? Like someone's using a wrong public key or anything, this will not check out, right? Everything has to be on point for us to receive a true here. And with these 3 functions, I can guarantee in communication that the sender of the message is the actual sender and no one has meddled with the message, right? For cross-chain communication, we don't want to rely on a single party. We want to rely on a set of parties, similar to validators in a blockchain. So we're using actually something called multi-signature schemes, right? Where we're going away from the single sender, but from multiple senders approving the same message. And you may ask, okay, why do I need multi-signature schemes? We have a short message, let's say 64 bytes, right? A signature of that message, it can also be longer, is pretty fixed at 48 bytes. Not a big deal. Avalanche consensus scales very, very well to large validator sets. On primary network, we have 1,500 validators today. So imagine every one of these validators signing the same message. That takes us to 48,000 bytes for a message that is shorter than 100 bytes. That is terrible, right? That's a very, very bad ratio. We have to transport a massive message with a massive signature just to deliver a little piece of information. So we are using BLS cryptography, which has a very powerful feature. We can take a bunch of signatures for the same message and aggregate it to a single signature of 48 bytes. It can be thousands, right? We can aggregate it, and the 48,000 bytes we just saw go back to 48, which is super powerful, right? And what does this mean? we just introduced two functions to our multi-signature scheme. One is aggregate signature. We put in however many signatures we want. We produce one signature. And the same for the public keys. We put in as many public keys as we want and create one aggregated public key. And we have a verify function, similar to the same thing before. We put in the aggregated public key, we put in the aggregated signatures, the message, and it will tell us true or false. Did this group of these public keys all sign this message, and were their signatures correctly aggregated? Then it works out. This is BLS signature in a nutshell. There's a huge scientific paper. I didn't come up with this, obviously, so I'm just taking the credit of some very smart researchers at Stanford. This is the base of Avalanche warp messaging. So when we look at the communication layer, what I just talked about is Avalanche warp messaging. We will go through it in a little bit more detail, how it works. After that, we're going to talk about Teleporter and the Cross-Subnet DApp itself, which are all in smart contract layer, right? So let's see, how can we use the cryptography that we just recalled for cross-chain communication? And we call this, as I said, Avalanche warp messaging, right? So first thing, very important, to understand the primary network, we have a P-chain, which is basically a registry of every validator in the Avalanche network. For every validator, think of it as a table, a Google Sheet, whatever, right? It's not a traditional blockchain, it's not a smart contract blockchain or anything. It's basically a registry of validators. We have their node IDs, we have their public keys that you just learned about in cryptography, and we have their stake weight, right? So we can look up in the P-chain pretty much every validator for every subnet, even if it doesn't belong to our subnet. So this is super powerful and solves a huge problem, as you will see later when we talk about cross-chain communication. So how does this work? We introduce this new role. It's called Avalanche warp messaging relayer, right? So what does this relayer do? We want to send a message from the source to the destination. First of all, the AWM relayer checks in the table that I just showed you, who are the validators of the source chain, right? I'm going to the table, I'm checking all the validators, who belongs to subnet A. Now, I am going to the source subnet validators. I have a message that I want to send. I'm going to ask not every, but the majority of the validators for their individual signatures. Has this happened? Did Martin vote for the DAO proposal A? Did Martin, deposit ERC20 tokens into the bridge contract? Whatever it is, right? I'm going to ask the validators, and they either going to attest or say, this never happened, I'm not going to attest to it. The AWM relayer takes the unsigned messages, the individual signature, aggregates them together. So the heavy lifting, the cryptography heavy lifting is not done on the validators itself, but on the AWM relayer. We get a message with the aggregated signature. This is the message signing. So now, the message delivery. The AWM relayer takes that message and posts it as a transaction, submits it to the destination subnet, right? Regular transaction. Uses a private key, signs it, says this is the message, okay. Now, the validators of the destination subnet have to verify that this is actually right. So they're going to do the same independently of the validator. They're not going to trust the validator to tell them who are the validator, the AWM relayer, who are the validators of their source chain. They're going to look for themselves. Who are the validators? They're going to aggregate the public keys, and they're going to check out if the aggregated signature is correct, right? So computationally, very, very simple, just a simple verify. Aggregation of public keys, simple verify. And then, if that is true, they're going to execute the message. If not, obviously, they're going to ignore the message. Someone has submitted something that is fraud, right? Okay, this is AWM in a nutshell. So let's move on to the next level, to what the developers are going to interface with. And I know it can be a little bit overwhelming, but I have good news for you. So this is a message flow. We have a cross-subnet dApp, Solidity. We have a Teleporter smart contract. We have the warp precompile that does all the magic. We have the AWM relayer, the Teleporter smart contract on the destination chain, a warp precompile, and a cross-subnet dApp. What does a developer interface with? we can forget about all this. Everything I taught you just a minute ago about aggregating signatures, like complex. If you want to build low-level cross-chain dApps, you will need to know it. It's good to understand it to have an idea what's going on in the end. But in your day-to-day building with Teleporter, you don't have to handle signatures. You don't have to handle anything. You're going to have to do two things. You have to call the smart contract of Teleporter, and you will have to enable your cross-subnet dApp to receive a message. That's it. And you will see how incredibly straightforward that is. Let's look at so we can think this is all we care about, right? Everything else is abstracted away from the developer, unless you're building more low-level stuff. You can, but you don't have to, right? So let's think about sending a message, right? So we're basically looking at this little error here. All we're doing here is we are importing the Teleporter contract. Do you have a question? Oh, OK. We're importing the Teleporter contract. We call the function send cross-chain message. We put some parameters in there. Most of them are optional. The only thing I have to tell the Teleporter is, what is the destination chain ID? What is the destination address, the smart contract I'm sending the message to? And the message itself, right? So this is a bunch of bytes. We will talk about this in a little bit. So all the fee info required, and the required gas limit. But the allowed relay, I can ignore that. That's all optional. We will talk a lot about it in a little bit. So that's all I have to do. Pretty straightforward, simple Solidity call. All the magic is done in the background. So what happens when I receive a message? I will have to make my cross-subnet dApp available, enable it to receive a Teleporter call. Teleporter does not know what your cross-chain dApp, what kind of function it has, what kind of argument it takes. Teleporter isn't aware of that, right? So what I have to do is, my cross-subnet dApp on the receiving chain has to implement a simple interface called receive Teleporter message. 3 arguments I'm going to get whenever I'm called. It's kind of like a callback, right? Where's the message coming from? What contract sends the message to me on the origin chain, and the bytes of the message. That's all I have to do, right? So very straightforward for dApp developers to use this. And all the magic, all this is done in the background. Let's talk a little bit about the message. We just saw how we send a single value, like a number. That doesn't give us too much, right? So we want to, obviously, we have all these fields of the Teleporter message, like the sender address, the destination address, all these kind of information. But obviously, we want to have some information on the dApp level, multiple values, packed in a single message. And how can we do that? We can do this pretty straightforward. Whoever is super familiar with Solidity, we can just use the ABI encode and ABI decode native functions of Solidity. Basically, what they do is we put in a bunch of values into ABI encode. We get bytes, zeros and ones, right? Then we can use ABI decode, put in the values, the types of the values we put in, and unpack it into the bytes, into the actual values, right? So when we look at Teleporter here, what happens? So on the source subnet, we're going to put our values here as an example, a string and a number, into ABI encode. We get the bytes. We put it into a message. We send it over to the destination subnet. It's very important to note this part here. On the destination subnet, we can't just, know what kind of values are packed. I need to know the types of the values that are in the message, right? To unpack the bytes, I need to know, there's a string and the uint in there. If I don't know that, it all's just gibberish. I don't know what it is, right? So if I know that, I have to kind of come up with a format between the source and the destination, what kind of values I pack. And then I can unpack them, call a function with it. I can also, do more sophisticated setups where I actually use, an identifier for the function and then different parameters based on the identifier. But that you can look up in an online course we're going to provide. So what are the features of Teleporter, right? One thing is we can rely on a relayer to, deliver our message, but we can also add an incentive for the relayer. So I can add to a message in ERC20, let's say, 0.5 USDC. And basically what I'm going to say is whoever delivers this message can claim that reward upon successful delivery, right? So these are all features. I can also do allowed relayers, so only certain relayers are allowed to deliver my message. So there are a bunch of features, advanced features in Teleporter. I won't go too deep into these. And now the final topic I want to talk to you about is load and trust. Right? So cross-chain communication is easy, but it is really hard to not create a bottleneck and create a trustless environment. So load first, let's think what happens. When I send a message on the source chain, every validator has to sign the message, right? Single validator, single signature operation, not very hard on the network. The relayer does a heavy lifting, signature aggregation, right? The destination subnet has to verify the aggregated signatures, therefore has to aggregate the keys, right? It is very important. There's no load on the primary network. The P chain is read, but we're not posting any trace of the message. We are not putting any record of sending a message anywhere on the primary network. This is purely between the source subnet and the destination subnet. Obviously, if the message is sent to the C chain or something, there will be a trace of it, right, because it's sent there. But if it's subnet to subnet communication, there's no trace of any message on the primary network. And this is super powerful, right? So there's no bottleneck, no if another subnet communicates, that will not have any impact on my load, on any how many messages I can send. It's completely independent. Two subnets talking to each other, completely independent of another two talking to each other. And then trust. So there's this famous quote, cross-chain communication is impossible without the trusted third party, contrary to common beliefs in the blockchain community. There are no trustless bridges, right? That's very important. Every bridge has to trust a third party. This may be decentralized, this may be a set of validators, bridge wardens, however you call it, but there's always a trusted third party. An Avalanche warp message also uses a trusted third party, but let's think who that is. And in Avalanche warp messaging, it's a P chain and the source subnet. And the beautiful thing about these two trusted third parties is we're already trusting them. If I'm not trusting the P chain, I wouldn't trust my own network. I wouldn't trust who are the other validators in my network, right? Like every chain has a record of the validators in them. If I don't trust it, there's no point in taking part in the chain. And I'm also trusting the source subnet validators. If I'm not trusting the source subnet validators, why would I want to exchange messages with them, right? If I'm not trusting the validators to be correct, to execute the transactions correctly, I don't have to trust the contents of the message either, right? So these are very important. We use trusted third parties, but we already trust them, and this makes the cross-chain messaging secure without introducing new cross-chain. So very happy to answer any questions. If you want to stay in touch, you can follow me on Twitter. Also, you can find me after the talk if you're more interested. And I'm also not only giving workshops about this, but I recently finished a course in Avalanche Academy, which is a free online platform, right? Anyone can enroll in it. And I just created basically the content we just saw, but with a lot of exercises, going a little bit more in depth. So if you want to test it out, please come forward. Happy to enroll you before the official release. Looking for people that are passionate about the topic, give me feedback, work a little bit with me on the exercises. So super happy. If you want to check out Avalanche Academy, you can find the link here. Can sign up for free. You won't be able to enroll yourself, but if you reach out to me, I'm more than happy to enroll you guys. And yeah.
When is it coming out?
The course?
The Teleporter?
Teleporter? OK, so Teleporter, we have two parts of Teleporter. One is subnet to subnet communication. It's live on testnet already. The other one is primary network to subnet. That's not live on testnet. I think it's coming next week. And I expect it to come to mainnet, I think, in 3-4 weeks. Yeah, but it's kind of pending with a D upgrade that's coming, I think, beginning December, maybe mid of December. Yeah, so very, very soon. If the number of validators is limited, no. So obviously there's at some point like a physical cap, but we are not like so. Right now we have, we have 1,500 validators today on the primary network, and the relayer has to aggregate them and all, but it's kind of like an off-chain computation, and since it's a single mathematical operation, like the signature aggregation is not a bottleneck, even though like. The bottleneck will be having all these validators in the system, but aggregating the signatures is like, let's say it's 10,000, 100,000 validators. Aggregating the signatures is the easy part. On the receiving end, you have to aggregate more public keys, but this is still, like I would say, computational doable for like signs of like 1,000 validators. The relayer can do it. The relayer can do it easily.
No, I mean on the receiving end. Who will?
Every validator of the destination chain will have to do the work, yeah. Because the relayer, but that's the case. Like if you want to verify something on the destination chain, you will have to verify it.
So it's a square. All the number of validators.
It's O from ON, so it's like with a number of validators. The aggregation doesn't. It's like a addition, not a multiplication. So it's just like 1 + 1 + 1. So it's not a square. It's not squared by every additional validator. It's just +1.
On the receiving end, each validator has to receive a message, get all the other validators, do the BLS calculation, make sure.
Oh, okay, I get your question now. Okay, so the validators on the receiving subnet don't have to communicate for this, right? No. We have the message, an aggregated signature, and the timestamp of when the p-chain lookup was done. So the validator are going to look up the p-chain at block height, whatever. Going to get the public keys. They already have it. They don't have to query it. They have it. Everyone is tracking the p-chain. Every validator is tracking the p-chain. And then they're going to aggregate the signatures, everyone for themselves. They don't have to communicate, and everyone for themselves can verify that the signature is correct.
How do you preserve order fairness? Sorry to monopolize.
Oh, no worries.
How do you preserve order fairness?
Order
How
fair.
do I know that the relayer is not going to favor your transaction as opposed to mine?
You will have to do that on the contract layer itself. So the relayer doesn't guarantee the delivery in a certain order. You can. So this is pushed up. So we kept Avalanche warp messaging as minimal as possible, as like low level as possible, to not introduce security risks. So a lot of these properties that you're talking about are not solved on Avalanche warp messaging, but are expected to be solved by the dApp developer on the thing, right? We don't want to overcomplicate it. Avalanche warp messaging is just aggregating signatures and verifying signatures at block heights. No message ordering, no retries, nothing. Teleporter introduced some of these, retries, retrying execution, allowed relayers, all this kind of stuff. But if you want to have order fairness, you will have to do that yourself, either as a higher primitive of Avalanche warp messaging, or just like on top of it on the smart contract level. Yeah? Yeah?
The relayer, there's a possibility of adding incentives.
Yes.
Right? So I think that the relayer is not just one instance run by, Avalanche, for example, but I can run my own relayer.
Okay, so the question is, who can run a relayer? How do I incentivize? Everyone, relayer is open source. Anyone can relay messages. I can relay my own messages, right? Like, so there is no secret sauce to the relayer unless, we restrict who can deliver the message. But if that is not restricted, anyone can do it. We could put this into a wallet that just, delivers the message directly of their users. But there could be 5 relayers for the same communication channel. First come, first serve. Right, like whoever, if there's a fee attached, a reward attached to the message, whoever delivers it first and is allowed to deliver it, gets the reward.
Sorry, one more question.
Last question, please.
Last question.
Okay, give him one.
I have another question.
I think he didn't have a question. Yeah.
The validator in this case can only ever validate a single check. A validator.
Yes.
Must it pick the C chain or must it pick a subnet?
No. So Avalanche subnets are, everyone is validating the primary network, C-chain, P-chain, X-chain. So everyone is tracking the P-chain, right? And then they can validate, there's no protocol limit on how many subnets can be validated. So you could, in theory, validate many. There is a computational gap, like no matter how heavy the machine is you have, there's the throughput, like the gap. But you also want to kind of like isolate the subnets from each other, because if one subnet fails, your whole validator fails, and you don't want to. Yeah, like you don't want to take them down. So what we're actually moving to is also subnet-only validators that are not even. Yeah. So right. So that's like ACP13. Whoever heard of it? Yeah, we're gonna have a more complex talk about that one. Yes. Right. Awesome. Thank you very much for the good questions. Whoever has some more, find me. Thank you very much.